Hi everyone. All right, welcome to the Calc 3 course. So you should have a blank set of your chapter 12. Sections 12.1 and 12.2 are together in this first set of notes. And recall that I'm going to be doing a video here that takes you up through example 1, and then I'll do another video that takes you up through example 2, etc. And all the numbers, all the examples are numbered 1 through whatever the end of our notes. I don't start renumbering them on the next section. So and that's the plan. Okay, so let's start with our section 12.1 notes. This is about three-dimensional coordinate systems. Cartesian coordinates for space are also called rectangular coordinates. Now when I say space, I mean 3D space, etc. It's often just called space. The axes that define them still meet at right angles, so you can kind of see down in here. The way to remember in which directions the positive x, y, and z axes point is to remember that this system is what we call right-handed. Okay, so first of all, what do I mean by right-handed? So if you're looking at this drawing, what we have is in the plane of your screen or the paper is the YZ plane. Okay, so this is the y-axis, this is the z-axis. If you take your right hand and you just make it flat and point it straight. So as you curl your fingers towards your palm, what you're supposed to envision is your fingers are the x pointing in the direction of the x-axis. So as you curl your fingers towards your palm, you're curling them towards the y-axis, and your thumb, as it's sticking out, is sticking in the direction of the z-axis. That's why it's called a right-handed coordinate system. There are left-handed coordinate systems, but for everything we do, we will do a right-handed coordinate system. So in the drawing, the x-axis is actually coming straight out of the screen or your paper. Unfortunately, we can't draw that, so this is how we have to draw it on a two-dimensional piece of paper. Okay, so draw this and try to understand a little bit about what's going on there. Notice that if I were to say I wanted to talk about the xy plane, you can say the xy plane. It also has what's called the standard equation z equals 0. That means the z component, z coordinate, is always 0 on the xy plane. The x and the y are anything. So it covers all x points, all y points, and we just say the equation z equals 0. The yz plane has a standard equation x equals 0, and the xz plane has a standard equation y equals 0, the same thought processes. So the three coordinate planes, x equals 0, y equals 0, and z equals 0, divide space into 8 regions. So in the xy plane, we had 4 regions. We called them quadrants, right? Well, in the three-dimensional coordinate system, we now call them octants. The octant in which the point coordinates are all positive is called the first octant. And there's really no convention for naming the other 7 octants. So what I've drawn up here is the first octant, okay? And these dotted lines are just to kind of give you a representation, a visual feel for how it's a rectangular coordinate system. We will deal with spherical coordinate systems, cylindrical coordinate systems. We will deal with other coordinate systems. The polar coordinate system you've seen already, but that's really for in the plane. Cylindrical includes the polar coordinate system plus adding z, and spherical looks quite different. So we'll talk more about that later. So remember, if you don't see a variable x, y, and or z in an equation or an inequality, then remember the coordinates for the variables that don't appear can be anything, okay, any numbers. So let's go through our first example. In our first example, we want to interpret the following equations and inequalities geometrically. So let's say I give you the equation z is greater than or equal to 0, and I say interpret that geometrically. So z greater than or equal to 0, first of all, it tells you x and y don't appear, which tells you that x and y can be anything. Okay, so then it just tells you that all the z coordinates have to be greater than or equal to 0. So what that is the entire what we call half space, which is all positive z or 0, so above the xy plane. Okay. When you see something like x equals minus 3, remember that means that y and z now can be anything, but x specifically can only be minus 3. So x equaling minus 3 is back in towards away from the screen. Again, we can't draw that, so we have to draw it kind of at this angled line here. So here's x equals minus 3 on the this is the positive x-axis, this is the negative x-axis. Now x equals minus 3, x can only be minus 3, but y and z can be anything. So again, I've drawn these dotted lines, but you have to imagine they can go infinitely in the y and the z directions. So it's the plane at x equals minus 3. perpendicular to the x-axis at x equals minus 3. Okay. If you see something like z equals 0, x is greater than or equal to, less than or equal to 0, and y is greater than or equal to 0, that tells you a lot of specific information. That's essentially the second quadrant of the xy plane, right? X has to be negative or 0, y has to be positive or 0. Z has to be 0, so it can't be going up or down anywhere. So it's just the second quadrant of this xy plane. Likewise, x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. That actually is back to our first octant. Okay. What if I see something like y has to be between minus 1 and 1, including minus 1 and 1? Again, no x or z. That means x or z can be anything, but y is restricted to being between minus 1 and 1. So that's the slab here. That's between the planes. Here's the plane y equals minus 1. Here's the plane y equals 1. Now it extends infinitely in the z direction and infinitely in the x direction. So I can't draw that on a two-dimensional thing. So you have to just visualize that it can go infinitely in those directions. But it can't go beyond y equals 1 or y equals minus 1. And if I see something like y equals minus 2 and z equals 2, that means that specifically y and z are set. But x can be anything. So if I plot the point where x is 0 there, so this is the point, remember these are all x, y, z, so the x is 0, y is minus 2, z is 2. Here's that point, right? You're at the origin for x, but you come negative 2 out on the y-axis, and you go positive 2 in the z-axis, and then this is where those guys intersect. This is the point 0, minus 2, 2. But x can't just be 0, it's anything. So you slide that point along the entire parallel to the x-axis, and it gives you that. So seeing something like this is actually a line. It's the line through the point 0, minus 2, 2, and parallel to the x-axis.